We were in the middle of section 2.2 when we left last time, and I believe we're on example 7. Does that sound right? Okay. Let me get to that point. Okay, we're going to use these 4 statements, and we're going to put a symbol in the blank. We're going to choose the symbols, between the symbols, is an element of and is not an element of. So remember, an element is an item in a set, something that's being described by a set. So the first thing, part A, or question A, says the empty set, blank, the set with 0 in it. That's what that really says, okay? Is that an element of the following set? Any thoughts? It's not an element of it. It's something else we encountered last time. It's a subset. And we'll get to the subset notation question. I'm going to do the same question here in a second. We're going to do with subsets. But this one is not an element of. Okay? So in order for the empty set to have been an element of what was on the right-hand side would have had to have had the empty set inside of those curly braces with it. And it didn't have that. We don't have that. So it's not an element. All right, part B has the number 15 on the left. And we've got to figure out what it's describing on the right. X such that x equals 2n, n is a natural number. Amy, what do you think that set's describing?
So if n is the natural numbers, which is starting at 1,
Mm-hmm.
right? So n, it would be 2 times 1, 2 times 2 times 3, and so it can't be an element of it because 15 is not a number.
Right. This is a fancy way of describing even numbers. Okay, so Amy said it really well. This says n is a natural number, 1, 2, 3, 4, 5, and so on. And this piece says that I'm supposed to be doubling all my natural numbers, which gives me the evens. 15 is not even, so this doesn't work. 15 is not an element of that set. Would 14 be? Sure would. C has an inherent problem in how it's actually worded, but let me actually look at the stuff that's on the right-hand side first. Okay? The right-hand side says 1 plus 2, 1 plus 3, 1 plus 4, 1 plus 5. Don't let that confuse you. Just figure out what those numbers are. What is the set that's on the right actually equal to? 3, 4, 5, and 6. All right, that's the set that's on the right-hand side. Now let's talk about what's on the left-hand side. What is that thing that's on the left-hand side? It's a set, isn't it? It's got curly braces around it. A set is not an element. So I don't care that there's a 4 on the left and there's a 4 in the little list on the right. It's not an element, right? It simply isn't an element, so it can't be an element of the following set. Now, if this didn't have curly braces around what was on the left-hand side, we'd be good to go, right? The number 4, as it stands alone, is an element. But when it's put inside those curly braces, it's thought of as a set. All right, what about D, 16? The set on the right. What's going on in the set on the right there? Yeah, it's counting by 2s. They're evens, right? So is 16 an element of what's on the right-hand side? Yes, it is. It's the only one that we got. Okay. They all fail for different reasons. So you have to think about how something can fail. You don't want to just look at one sort of category of ways that something can be messed up. There's more than one way that it can fail. All right, we're going to do the same thing. I mean, the problems look exactly the same, but the answer choices are different. So the first answer choice given there is the subset one. Okay? Subset. The second one with the line through it, I didn't actually define that, but I'm going to guess you know what it is. What is it? It's not a subset of. Right, not a subset of. So let's take a look at the first one. Hannah, you wanted this one the last time, didn't you? This one's a subset, isn't it? All right, we talked last time about the fact that the empty set is a subset of everything, right? We can talk about the subset of infants in my house and how wonderful they are behaved. It's the empty set. It'd be weird to talk about it, but it is a subset of them, right? In my house, I'm serious. Nobody does a lot of things in my house. Nobody leaves sticky handprints everywhere. Not me, not nobody, not me. That's his name. His name is Not Me. Does Not Me live in your house? I bet he does. I bet if I asked your moms would say that he does. He lives in your house too. Who left the refrigerator open? Not me. Who didn't feed the cats? Not me. No, not me. All right, so empty sets. They're good. They're good stuff. There's a set. How about B? Is 15 a subset of the even numbers? No. And it actually fails even before I said even numbers. Why is this not a subset? Do you know? It's not even a set itself. Now, if I could put curly braces around it, it would be a set, and then we could answer the question from a different perspective. But it's not a set at all. So this one doesn't even make sense to talk about that way. C, is C a set on the left? Yes, it is. And we talked about on the last slide that these are the numbers 3, 4, 5, and 6. So is the set with the number 4 in it a subset of the set 3, 4, 5, 6? Yes, it is. We talked about those last time. We hadn't done an exact example yet, but this is an example of a subset. Not a very exciting subset. It's a set with one person in it. Committee meetings are not very exciting if you're the only one who shows up, okay? But this would be a subset. How about D? Why does this one fail? It's not a set, okay? Now, I will say that your book will just have you fill in the blanks. They're not going to have you say why it does or doesn't work. I get that. But in the past, when I ask questions, I make you explain why. I want to know if you're thinking about it from the right perspective. So make sure when you're looking at it, you know why it's failing, okay?
So if that one would have had the little curly things around the 16, it would have been.
You're right. If it would have had the curly braces around it, it would have worked. You got it. Okay, fundamental counting principle. Sort of innately, you know that this is a true statement. So we're going to go through it, and you're going to be like, yeah, I've seen that happen before, probably. The fundamental counting principle says the following. If an event M can occur in little m ways, and event N can occur in little n ways, then event M followed by event N can occur in m times n ways. Okay? We use this in mathematics all the time. We used it in proportional statistical reasoning. We've used it in geometry already this semester for my students in geometry. And here's a classic example. We've got all ladies in the class. So we're going to create outfits. Okay? We're going to assume that all of our color scheming works. So these are all wearable outfits. We have 3 shirts, 4 skirts, and 5 pairs of shoes. And the question is, how many outfits can be created? Well, according to the fundamental principle of counting, all we have to do is to multiply these numbers together, and that will tell us the number of outfits that we have that we can create. Because there are 3 different shirt options, there are 4 different pants options, and there are 5 different shoes options. Not pants, sorry, skirts. Okay, so what do we get when I multiply these together? 60. So there are 60 outfits. Okay, another example of this. We're going to go to the mall, because where else are we going to buy our clothes, right? Yeah. All right, so we have 6 favorite stores in the mall. In how many ways can the following happen? A, you have time to go to only 3 of them. So see, over here I wrote 3 lines because my outfit would be incomplete if I wasn't wearing all 3 of those things. Would you agree? Yeah, got to have one of them all on, or somebody's probably going to send me back to my house and say, go get dressed appropriately, right? That's what I say to my son when he tries to leave without one of those things on. Shoes. Yesterday it was shoes. All right, so we're only going to go on this one, though, to 3 stores. So I'm only going to draw 3 lines. Make sense? I got lots of favorite stores, but there's only 3 of them that I'm going to go to. So I have how many different options that I could go to if I go to my first store? 6. And in sort of understood in the problem, we're not going to one store more than once. It doesn't make sense in the context of what's going on. Sometimes it makes sense that you have the options to happen again, right? So, you know, if you were eating cookies and you ate a chocolate chip cookie, you'd still have an option to have a chocolate chip cookie as a second cookie, those kinds of things. But this one doesn't make sense to go to the same store again. You were already there. All right, so after you go to the first store, There's only 5 choices, right? And then after that, there are 4 choices. So we have 6 times 5 times 4, which gives me how many different choices or ways in which I can go to my 3 of my 6 favorite stores. 120 is correct. So there are 120 ways or options. What if I get to go to all 6 of them? How would the problem change? You'd have 6 lines. And what would the numbers be that would go on these 6 lines? 6, 5, 4, 3, 2, 1. And if I multiply these numbers together, what do I get? That is right, 720 ways. All right, and we'd already done example 11, so that puts us at the end.